Okay, hello everybody, and welcome to our seminar today. Today we are going to go through the characterization of fracture complexity, fracture type, and anisotropy in laminated formations. So for this work, a series of laboratory true-triaxial hydraulic fracturing tests were carried out in shale outcrops and core a deep specimen from the Montney Formation. The test reflect in situ like open hole fluid injection at depth. The test scheme aimed at assessing the impact of flash and anisotropy in intermediate stress and fluid viscosity. Another key aspect was to assure the strength anisotropy through an innovative subcoring method to obtain testing plots. The formation of fractures opening against the sigma 2 instead of the sigma 3 in the true-triaxial hydraulic fracturing experiment defies the dogmatic expectation that the fractures will always propagate against the smaller of the minimum principal stress direction at minimal the tangent stress. The results are a clear indication that the tensile strength and anisotropy plays an equally important factor to the in-situ stresses with respect to the stress initiation and propagation. The outcome of this experiment work is a new conceptual model that is not tied only to the magnitude of the in-situ stresses, but rather identifies the plane with minimal mechanical resistance defined by the magnitude of the principal stress and the anisotropy in the tensile strength of the rock material. Another important result of this experiment program confirms that influence of viscosity on the complexity of the associated fracture network. Additionally, it also highlights the significant importance of obtaining mechanical strength parameters to understand the material anisotropy. And for this talk, we have with us Dr. Aly Abdelaziz, who is a geomechanics expert at Geomechanica Inc. Dr. Abdelaziz holds a Bachelor of Science in Civil and Structural Engineering from the Benha University in Egypt and receives his PhD in 2023 from Professor Brazelli's Geomechanics Group in the Civil and Mineral Engineering Department at the University of Toronto here in Canada, where he also works as a postdoctoral fellow. He has over 8 years of professional experience in the field of geotechnical investigation and construction monitoring and material testing in an accredited laboratory in Dubai. His research interests include numerical representation of synthetic rocks using a partial Voronoi tessellation and measuring of influence of machine on strain during tests. He also works on true-triaxial hydraulic fracturing tests to develop an understanding of rock stimulation in the context of fracture types and well as its complexity. So just join me welcoming Dr. Aly, and Dr. Aly, the podium is yours.
Hey, thank you so much, Daniel, for the introduction, and thank you to the University of Alberta Geotechnical Center and the seminar series for inviting me today. Excuse me. And hopefully this talk will be informative and engaging to everyone who is attending. So as Daniel alluded, I'm currently a geomechanics specialist at Geomechanica Inc, and I graduated from the University of Toronto just shy of a year. The presentation I'm going to present today has the university logo because everything that is presented here was done during my time at the university. And the presentation here would have not been possible without our sponsors, and as well as the contributions from Mr. Ha, Dr. Nasiri, Ms. Lay, Mr. Maxbook, and Ms. Yu, who are all part of the work and will continue on with the work that I will present today. So today we're going to talk about characterizing fracture complexity, fracture type, and anisotropy in laminated formations. And for this, what are laminated formations? These are just examples from all around the world. You have the Montney, the Vacamorte, the Eagleford, the Marcellus. What we notice in all of them instantly is the bedding planes or the discontinuities that are in them. So we need to understand this to feed our numerical models. So if we look here, these are different reservoirs or different types of discontinuities. And as we see, the change in stresses will impact the propagation of the wave, in this case, rock stimulation. So two things now are important: the magnitude of the stresses and their orientation with respect to the discontinuities, or the discontinuity and their spatial distribution. So let's look at this, the Montney Formation. And the reason we have the Montney Formation today is just because it is the largest unconventional hydrocarbon play in Canada. And today, there is no studies on the hydromechanical characterization under true-triaxial conditions for the Montney shale. In fact, these are very rare, if not non-existent, for deep reservoirs. And although you look into literature, there's public available data every now and then for shale samples at depth. And this is also true for almost any fragile and water-sensitive rock at depth, which we will show as we move on. Just to talk a little bit more about the Montney, and because we spoke about the stress state. So the stress state in the Montney is a strike slip. So sigma V, or the horizontal stress, is the intermediate principal stress. So let's take this context and put it in the context of the experiment that we will show as we go on here. So given a strike slip regime with a horizontal wellbore, classical theory expects it to fail against the least principal stress, which is sigma 3. So we expect the shut-in pressure or the fracture opening pressure to also be equal or close to sigma 3. So this is the experimental setup. Let me just pull up my pointer. Yeah. So this is the experimental setup that we have. Sigma 3, it's horizontal wellbore. Sigma 2 is your vertical stress. And then we inject water, or however you wish to stimulate your rock. We are expecting, based on conventional theory, that it will break against sigma 3, or it will fracture against sigma 3. However, consistently in our results, we found this, that it was fracturing against sigma 2. Now, because of this, we had to pause and reassess a lot of things. And by reassess a lot of things means we had to go back to literature and look at data that was available, which we found were non-existent. And by data, I mean mechanical test data. So now we have a test where we are breaking against sigma 2. But to understand this test, we need to overcome these two obstacles, which are limited and biased laboratory tests arising from sampling procedure, and the variability of the results for similar samples across testing laboratories. And what I mean by this is, if you go into literature for almost any type of reservoir rock, you will notice that most of the tests were done parallel to the bedding planes, as you see here with the green. So in this direction, because the cores that come out, you are able to recore them or replug them as typically in the oil and gas and test them. However, when you try to test in this direction and in this direction, this is usually what happens. So you start getting disking. So that's one problem. The other problem is because you only test in one direction, you are biasing your results. So your limits to the results are in the two extremes. So parallel to bedding and maybe perpendicular to bedding. So you really are not evaluating the anisotropy in any way. So we have two issues now. The first one is, how can we obtain samples? The second one is, how can we get good results that are independent of the machines? So to answer the first question, since most of these rocks are sensitive to water, we had to find a way where we didn't use water. That's number one. Number two, we realized that the coring process itself causes some stresses on the rock that cause it to disk. Now, there are other methods out there, for example, the SINTEF method, where you apply a normal load. But we tried to go outside the box, or to think outside the box. What if we used, for example, here, a milling machine? So a milling machine with a milling bit at the end, and then cool it with cold air. and then you have a dust collector that collects whatever is coming out, or the debris that's coming out. And surprisingly enough, we were very successful. And by very successful, I mean that we were able to obtain pores. So you see that we were able to obtain perpendicular to bedding, parallel to bedding, and 45-degree to bedding. In fact, prior to this research, or prior to this work, there was only one data point at 45 degrees. Now we have 2 samples that we can test. So first problem we've overcome is we were able to capture, or we're able to overcome the problem associated with sampling, and we were able to replug and obtain samples that we can test. Now, the second question that comes, when you test samples on different laboratories, you start getting different results across. So we needed to look into this more deeply and understand what is the impact of the machine and what does it have on the test itself. So what we decided to do is we brought a aluminum 6061 temper 6. So it's a very well-known material that has a predefined or a well-defined elastic modulus of 69.7 when it's extruded. So before we start our test, we know for a fact that this material is supposed to yield 69.7. So here we put our aluminum on system number 1. So this is an MTS system. The load cell is at the bottom, and we capture strain using 2 devices. The actuator, movement itself, up and down, and the movement of the LVDTs. So we capture strain using 2 methods. So in this case, what you see is the global is the whole system, so the actuator, and then the blue one is the LVDT. So the first thing we notice is both results are not anywhere near the theoretical line, but the actuator gives a much lower strain than the LVDT, but again, they're still far away from the theoretical line. So we took the same sample out, and then we put it on another machine. In this machine, it's a different setup. It's a concrete frame. However, here they have 3 LVDTs. Point being, we still are not near the theoretical line. So in this case, we produced the pinkish line. So what we understand from this is every machine has inbuilt strain in it that we call system compliance. Hence, we need to understand this compliance. We need to understand how much strain is in the system or is being captured by the strain measurement devices and subtract that from our strain results. So basically what we need to do is, if you were testing on system 2 or system 1 with the blue line, whatever values you get, you were supposed to correct by 22% to bring it back to almost to the yellow line. If you were testing by the actuator, you would have to change it by almost 56%. So it is underestimated by almost 50%. So we really need to understand the implications of this and understand that if we test different rocks or the same rock on different machines, we are bound to get different strain measurements. If we use different strain measurement devices for the same machine, we are also going to get different results. However, if we understand the system compliance of every single one, we will be able to see or to note that they are actually really much closer than we think. So we saw the problem of getting the sample. We started looking at the results a bit more in depth in terms of analyzing their elastic modulus. And so we tested an array of samples. So over here on the left, you see the maximum stress or the UCS versus the bedding plane orientation. In fact, the stress is at different confinements. You see the elastic modulus average and the Poisson ratio. I want to highlight the following is because we have data at 45 degrees, now we can understand or look at the anisotropy a bit more. So you see that when there is no confinement, there is a linear trend or there's a linear loss in strength from parallel to bedding to perpendicular to bedding. However, when you have some confinement, you start seeing that all the strength at 90 degrees are almost the same, give or take their variation, or the variation at 90 degrees is much lower than at 0 degrees. And at 45 degrees are actually lower. Now, unfortunately, in our case, we did not have more rock to test different orientations, but I am sure that if you get different orientations, you will get a much better understanding of the anisotropy. I also want to draw your attention to the elastic modulus. So what we see in the elastic modulus is at 0 degrees, if we're testing parallel to the bedding, the variation in the strength or in the stiffness is almost 5 MPa. However, when you look at it at 90 degrees, when you're testing perpendicular to bedding, the variation is less than 2 or 3, GPa in this case, I apologize, 2 or 3 GPa, irrespective of the confinement. So let's have a slightly better look or understanding of what's happening here. So when the elastic modulus is, or when we're testing parallel to bedding, let's assume that these are basically columns of different stiffnesses connected by springs. When you have no confinement, there's nothing that really holds them together. But when you have some confinement, you're not allowing them to move. And thus, you get this variation in the results. But when you have 90 degrees to bedding, so you are testing perpendicular to bedding, what you see is the confinement doesn't really have any impact on your springs. So the stiffness is almost the same, which is what we capture here. Now, that being said, we also want to understand the difference between the the UCS and the Brazilian disc, or the indirect tensile strength of the rock. Typically, we use 0.8 or 8 to 10. But here we started looking at it in a different perspective. So here we plotted it in what's called the modulus ratio and the strength ratio. But what I want to highlight is the following. If you look at it in the strength ratio, you will realize that if you are testing, or if your sample, or if the orientation of your fracture is 90 degrees to bedding, the ratio is 20. And if you are 90 degrees or perpendicular or parallel to the bedding, you are at 15. So numbers that are completely different from the norm that we typically use in our geomechanics or geotechnical fields. So we've looked at the unexpected issues that we had, which is sampling. We were able to obtain samples. We were able to understand the response of the machine, and thus we are more confident about our elastic modulus numbers. We're also able to assess the tensile strength in different orientations and understand that the ratio that is common in textbooks is not actually what we capture in the lab. Plus the fact that for different orientations, there's a different factor. So keeping all that in mind, let's go back to the initial problem, which is, why is our fracture opening against sigma 2? And since it's open against sigma 2, can the shut-in pressure tell us a lot more about the principal stresses than we typically know? So for this type of test, we decided to go with 2 different rocks. So an outcrop rock, so this is from a quarry on land, and then a sample from depth around 2 kilometers below ground. So 2 different types of samples, and we decided to test them in true-triaxial conditions. To do this, we need 2 things. We need to understand the stress state, which we were lucky enough that a Montney 1D mechanical earth model is available. From there, we were able to capture or to understand the stress state at 2 kilometers below ground. We need a reservoir rock, which we have 2 types now, and we need injection fluid, which in the case of the experiments that we'll show later on, we have water and we have high viscosity fluid. And on the right here, you see the magnitude of the machine. So this is me on the other end, and it is a huge machine. So in the true-triaxial machine that we have here at the University of Toronto, we will talk about it in details in the following slides. So this is the case of the setup that we have. So this was the injection hole from top. These are the bedding planes. And then each surface has 3 sensors for AE and for PNS wave. The machine can apply sigma 1, sigma 2, and sigma 3 independently. In fact, each one of the actuators can move independently. There's 3 LVDTs that run across every side. And as you said, 6 faces. Every face has 3 AE sensors. And these are the specifics of the AE sensors. This is the top of the assembly. And this is the rock inside. And this is how it looks inside the machine. This is a closer look at the machine. So this is the packer that's inserted here. And this is this sample holder is inserted into the polyaxial cell. And this is the polyaxial frame. Now, what we are expecting is we're expecting to see something like this, which is the textbook explanation of what a hydraulic fracture looks like. You have an initiation pressure or fractional initiation pressure, propagation pressure, NIAS IP, and a closure pressure towards the end. Again, based on the configuration that we have here, sigma 2 is this way, sigma 3 is here, so we're injecting this way. Now, moving on to the results. So this was the outcrop sample injected with water. And as you can see, the stress state, sigma 2 is 42, sigma 3 is 37, and sigma 1 is 54. And this is the tensile strength anisotropy. So in one direction, it's 12 MPa, in the other direction is 18. And we injected water at 7 milliliters per minute. And this is the result we got. I'll spend some time here, a couple of minutes, just explaining what is happening, because we are going to repeat this for several other tests. So the blue line is the injection at 7 milliliters per minute. The red line is the pressure response at the injection, so just above the injection hole. These gray lines are sigma 1, 2, and 3 respectively. Now, in this case, we have what we call a classical result, where we have cavity filling, followed by open hole pressurization, then a pressure ramp up until you reach a maximum pressure, then unstable pressure relief and fracture propagation until at some point you reach a steady state pressure, right? But we have the luxury now of looking at this in much more detail. And by much more detail, I mean, let's zoom in here. So in this specific test, we know that we broke the cube in one fracture that is perpendicular or that is against sigma 2. So this is our sigma 2, this is the sigma 3 injection, and we know that there is one break. What we see here is just a blow up of what is happening. So this is the pressure build up. Then you have sigma 1, sigma 2, sigma 3. You have the pumping rate. But also what we show here is the displacements. So this is a displacement in the sigma 2 direction. This is the displacement in the sigma y direction, sigma 1 direction. What we see here is this. So the solid line is each data point not smoothened as captured by the LVDT. The dotted line are the averaged displacements. So we see a significant drop in the x direction, which means that it is actually opening in the x direction, which confirms this. Now, the drop here was substantial. So we decided to look at the next substantial drop in terms of stress and probably try to see what happened. Over here, we see the same thing. We see some movement in the x direction, which could be the secondary fracturing opening. But what we do capture is this. What we see here is the pressure rebound, or the pressure after the breakdown has happened, is somewhere between 1.16 and 1.4 MPa per second. So this is a signature that we've noticed in anything that has a huge drop in terms of pressure. Let's look at some other locations where there is a drop, but it's not that significant. So you don't see a red dot with the displacements just because there is nothing substantial to note. And we see that the pressure response or the pressure recovery is much different. So in this case, it's 0.1 almost 0.5 or 0.4 MPas per second. So now we have two different types of signatures. One where we have movement in the X direction, a significant movement, followed by a pressure recovery of almost greater than 1 MPas per second. And then we have a second type of signature where there's almost no movement in terms of the LVDTs, and the pressure recovery is much less of 0.4 MPas per second. Now with advanced serial sectioning tools, we were able to inject the cube with epoxy, a fluorescent epoxy, and grind down the cube to get layers of images at 50 microns, and then using machine learning techniques, stitch it back. So you were able to produce this fracture map. I invite you to read the work by Lay et al. That describes this work. So what we see here is sigma 2, sigma 3, sigma 1. And if we zoom in, we start seeing these fractures that initiate from the borehole. We start seeing shear-like fractures, initial fractures. We start seeing arc and graben features where the pressure, where the injection, or sorry, where the epoxy is trying to go in this direction. And we see that a lot. And we could attribute this to the small bumps that we have in our pressure curve. Now, we've understood what is happening, or we've developed an understanding of what's happening with the outcrop cube. So next we move to the core at depth. So this core now is at 2 kilometers below depth. Before we start, this core was scanned, and we know that there is a pre-existing fracture running through it. So this is known beforehand before we start the test. This sample here was cut in 2 cubes and to do the true-triaxial test, and the 2 cubes, one was injected with water, one was injected with high viscosity fluid, in this case, soap. So let's have a look at the first one. So this cube was injected with water. You see the black is the pre-existing fracture, red is the bedding planes, and the green is where we got the fracture or the hydraulic fracture. So once again, opens against sigma 2. And the stresses here are slightly different. So sigma 2 is 29.1, sigma 3 is 23, sigma 1 is 41. And we get the pressure curve. Again, injection is at 7 MPas 7 milliliters per minute. And we look at the pressure response. In this case, we had 3 cycles to try and understand what the reopening pressure is. So let's have a look similar to the first time around, or the outcrop cube, to see if we can capture any of the signatures that we were talking about. So over here, we don't see any abrupt movement in terms of the LVDTs, although there is a drop in the pressure. Similarly here, what we see is just normal movement. There is nothing really abrupt. Again, just movement, nothing really abrupt, nothing really open. So what's clear here is these 3 movements indicate similar to the outcrop cube, where we had shear-like movement developed within the cube. So we keep this in mind, that in this case, we only had mainly shear movement in the cube. But what we also notice is the difference to the, like in this case, the reopening pressure is really close to sigma 3. This is third cube. So in this cube, we had the similar stresses for the outcrop, for the sample at depth. And we injected it with high viscosity fluid. We look at the pressure time curve. And then over here, we start seeing different response. So what you see here is an abrupt movement or a sudden movement in the X direction, which would indicate that it's opening against sigma 2. And a similar behavior here. But what we do notice is the time it took from this drop as compared to the time for this drop, this one had a huge lag, I think around 5 seconds. In this case, it was almost 3 seconds. So it's much faster. Now, I know I bombarded you with lots of numbers, lots of signatures, but let's look at this in a nice figure. So this is what we have in terms of the stresses. So for each cube, you see sigma 1, 2, and 3 that were applied on the cube. And you see the shut-in pressure. Now, the shut-in pressure is an indication of a fracture reopening pressure. Now, in this case, it's almost equivalent to sigma 2. So in this case, we know that we have one single fracture that is equal to sigma 2. Sorry, against sigma 2. However, in these two cubes, they are all over the place. Here it's less than sigma 3. Here it's greater than sigma 2. What we can say about this, though, is that there is fracture complexity. When you have water, which we see here, we haven't really created that many pathways. But when we have high viscosity fluid, we actually created a brand new fracture in this direction. And in this case, these are the bedding planes, and the gray is the pre-existing fracture in the core before we started. So the shut-in pressure, if it's one fracture that's against one of the principal stresses, the resulting shut-in pressure should be equal to the principal stress. So as we see here, it is not necessarily sigma 3, but it is one of the principal stresses. We look into this from a different perspective now. What about breakdown pressure? So the maximum pressure that was reached. In the outcrop cube, it was over here around 50. And in the two samples at depth, it was almost in the same, more or less, number of around 32 MPa. Now, what we bring to the table here is if it was to open against sigma 2, you're expecting the breakdown pressure to be these crosses. If it was to open against sigma 3, it was expected to be these yellow diamonds. So what's clear here is that the tensile strength anisotropy plays a great role given the stress rate that we had in this experiment. So because the tensile strength anisotropy is so high compared to the stress isotropy that's like the in-situ stresses that's being applied on the cube, we have this flip. So it is expecting, or it is finding it easier to break against sigma 2 than it is to break against sigma 3. So with this, we brought forward a proposed breakdown model that actually honors the rock strength anisotropy plus the in-situ stress. So you have to consider both. It is not just sigma 3, it is not just sigma 2, it is not one tensile number. There is several tensile numbers, and the in-situ stress is different for the different directions. So we have to understand that the summation of these two numbers is what the rock is trying to overcome. We've also shown that we have unique breakdown signatures. So with tensile, you see really an abrupt movement. And when you have high viscosity fluid, there is a lag between once the initiation happens and once the LVDTs subside to move. And when we have shear, there is not really any strain response, or there's no LVDT movement. We've also shown that the shut-in pressure can be a proxy to determine the complexity of the fracture. So if you have a planar fracture, you're always going to resolve against a magnitude of 1 of the principal stresses. And then with high viscosity fluids, you get a much better hydraulic fracture, but you also limit the interaction with the pre-existing weakness planes and the discontinuities. Now, this work does not stop here. What you can do with this work is you can actually build more information now that you have all the details of all the fracture maps, of all the fracture networks, and then try to understand that the stimulated rock volume is dominant by the bedding planes in this specific case, while the bi-wing fractures have smaller apertures and volumes. So we can start to understand what is the fracture class volume. So we see that there is more bedding plane parting than bi-wings and natural fractures that have been stimulated. We can also look at the fracture aperture and see the differences between the three, where the bi-wing fracture has a much lower fracture aperture as compared to the other two. So this work is just a start to hopefully more work in trying to understand the mechanics of the true triaxial response of shale under reservoir-like conditions. And with this, I would like to thank you for having me, and we open the floor for questions.
Okay. Thank you very much, Dr. Ali. Any question here in the room? Of the people that is online, you can please raise the hand and you can ask. Okay, meanwhile, yes, I have two questions. Oh, let me look for those. First is regarding the compliancy determination that you did using the aluminum piece.
Yeah.
Any thought or any elaboration that you can do about the rate, the strain rate, and how that strain rate affects and can affect that determination of the compliancy of the system?
Sure. So typically, if you are testing according to the ASTM standard or the ISRM standard, they typically advise that you reach breaking of rock between somewhere, I think, 2 minutes and 15 minutes, if memory serves me right. If you look at strain rates for typical rocks, that's somewhere between, I would say, 0.05 to 0.2 millimeters per minute. If you test your aluminum at any rates in between those, you will get very similar results.
Okay.
So to answer your question, as long as you're within the quasi-static range,
yeah,
it should be almost the same. Not exactly the same, but really close to each other.
Okay, perfect. And my second question is regarding the so-called shallow stresses. When you create a fracture and you pump anything into that fracture, it's well known that when you are going to create your second fracture, you get those shallow stresses, which mean like a kind of local redistribution of the stresses that push the material. So now it's not a problem of constant stress, but a problem of constant strength. I don't know if you have planned any second phase of this kind of test in laminated materials to analyze those kind of shallow stresses and how they affect the aperture and extension of those fractures.
Okay, so to answer your question, I don't, but there is a student in the group who will take on this project further. But for our tests, we did around 11 tests, and all of them gave the same result. The machine is put in stress control once you reach the desired stress. So it is allowed to move. The pistons are allowed to move back and forth. Right? So it does allow for that relief. And if you look at the stresses in the time domain, you can see that it is allowing for the stress relief, if I understand your question correctly.
Yeah. Okay. Yeah, thank you very much. Anyone online or everyone here in the room? Okay. I guess there are no more questions, Dr. Ali. So thank you very much for being here. And yeah, great presentation.
And thank you for having me again.